Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC Point-Set-Topology Part-II. Today we will start studying manifolds with boundary. Last time we studied what are called as manifolds, right? So this manifold with boundary, they are also going to be manifolds. Actually, we are going to extend the definition of manifolds to a larger class of topological spaces. So I will touch upon this usage of this terminology a little later. The first thing is that we are already familiar with the word boundary in a different context. Namely, we employed this whenever you have a topological space and a subset of that. The boundary of the subset A is defined as the closure of A minus the interior of A. This nomenclature for the boundary is totally dependent on the larger topological space X, wherein the subset A is sitting inside. Now the term boundary will be used in a much subtler way, in a technical sense, okay, and it is going to be an invariant of the homeomorphism type, and it does not depend upon where the manifold is sitting inside. Okay, so having said that much, let us come to brass tacks here. The important thing here is, even to make this definition, we need the full force of Brouwer's invariance of domain. Namely, you remember this one, not the weaker form but the stronger form. Namely, if you have two non-empty open subsets of Rn which are abstractly as topological spaces, namely take the subspace topology from Rn. Suppose they are homeomorphic to each other. If one of them is open, then the other one is also open. This is a completely non-trivial statement, a profound statement, and this is what we will need. We have used only a weaker version here, namely Rn and Rm cannot be homeomorphic if M is not equal to N. That is an easy consequence of this one. Okay, so now we will need the full force of this. I will come to that again, why we need it. So first of all, our model for manifold itself will change now. Earlier the model was Rn, or equivalently the open disk inside Rn, right, the unit disk inside Rn, because both those two are homeomorphic to each other. Now we are taking the half space Hn, namely the subspace of Rn, such that the last coordinate of the points is bigger than or equal to 0. You can take any other coordinate, this is convenient one. Only the last coordinate is bigger than or equal to 0. So this is like the ray, half ray from 0 to infinity, half line, 0 to infinity open. Okay, when n equal to 1, this will be precisely 0 to infinity, 0 closed, infinity open. So we are allowing that boundary point 0, the boundary in the older sense, namely this point 0 will be a boundary point of the closed 0 to infinity inside R. Okay, that is the starting point. That is our model now. So in Hn, for example, all points wherein the last coordinate is 0, that is subspace of that is going to be the boundary of this Hn inside Rn. But once we have taken this one, you can just forget about Rn and use this model Hn to define our manifolds. So let us see how. Let us start with the topological space X. We will call it a manifold with boundary. So I am not defining manifold, I am not defining boundary, okay. I am not defining in the word with here, but I am defining manifold with boundary, this entire phrase as one single technical phrase. So a manifold with boundary, if it is second countable, Hausdorff, and the local Euclidean part is modified here now. For each point x inside x, okay, we have a neighborhood ux and a homeomorphism phi from ux to Hn. Now you can take this as the whole of Hn also, no problem, on to an open subset of Hn, that is more convenient, that's all. We know that just like ux to Rn I could have taken in the case of ordinary manifolds, right, or ux to open subset of Rn, or ux to just the open disk Bn, those three things were equivalent. Here also in the homeomorphism could be ux to the whole of Rn or some open subset. Okay, this open subset allows us a little more freedom. Terms such as charts, coordinate functions, coordinate neighborhood, atlas, etc., which we have defined in the definition 12.1 of manifolds. Remember that in the context of manifolds, they all make sense exactly similarly, except that now the coordinate functions phi of ux, it is not necessarily an open subset of Rn, but it is actually an open subset of Hn. This is something funny here. In fact, every open subset of Rn has a copy, an open subset inside Hn, but not the vice versa. So Rn itself is homeomorphic to the strict open upper half space here. Namely, take all points such as last coordinate is strictly bigger than 0, right. So if you have an open subset of Rn, that will be homeomorphic to some open subsets of Hn strictly contained inside the interior of Hn. Alright. So this half space has more open sets than the full space. Anyway, so we can have this extra open subsets here of Hn which may meet the boundary, which may meet the plane Rn minus 1 cross 0. That is the extra thing here. Therefore, this is clearly a generalization of the old definition manifold. Okay. Let us denote by interior of X the set of all points X having a neighborhood Ux homeomorphic to an open subset of interior of Hn itself. You see, there are two parts. One may be just Hn, but this is a stricter condition. Interior of H, homeomorphic to interior of Hn, okay, namely all Xn, the nth coordinate bigger than 0. So take such points, then they will form automatically a manifold, a topological manifold in the old sense, right. So why the interior is non-empty as soon as X is non-empty? That is also clear, because as soon as X is non-empty, there is some open subset which is homeomorphic to a non-empty open subset of Hn. Okay, if you delete the boundary part here, that will be an open subset in the interior of Hn, which is obviously non-empty. So everything you have to see inside Hn, then you get this one. Okay. The complement of interior of X in X is denoted by boundary of X. So this is a notation now. I will read it as boundary of X, and is called the boundary of X. So we had used this notation earlier for boundary of A, where A is a subset of X. If X is the topological space in which boundary of X is taken, then this is empty. So this has no other meaning there, right? Because the closure is whole of X, interior is whole of X. So boundary of the whole space inside itself is empty. All right. So here that is not the case. X is the space; it is not contained in anything. Okay. This is a topological space on its own. Now boundary of X consists of those points which are not in the interior of X. So interior of X also has a different meaning here. Okay. So this is in the general topological case, interior of X inside X would be whole of X. That is not the case here. Here also it can happen that, but then X will be a pure manifold, not manifold with boundary. Okay. So I am talking about this one. It may happen that boundary is empty, just like in the case of manifolds. Okay, which means that X is precisely manifold. This is if and only if. The points of boundary of X are characterized by the following property. So this is where you have to be, you have to use the Brouwer's invariance of domain. Namely, there is a neighborhood Ux of X in X such that we have a homeomorphism phi from Ux to Hn onto an open subset Vx of Hn such that the nth coordinate of this point, nth coordinate of Vx, this itself vanishes. So the Rn minus 1 cross 0 should be hit by this phi. Okay, take such a point such that phi x is inside the Rn minus 1 cross 0. Okay, so those are the boundary points. Now, what do you mean by characterize? Let me tell you that. Okay, so this is where I have to use the Brouwer's invariance of domain. So let us see, start with such a point. Now suppose there is another neighborhood Ux prime and another homeomorphism psi from U prime X to Hn, similar to that one, onto an open subset Vx prime of Hn such that the nth coordinate Vx is now positive. Either it is positive or it is 0, right? It is greater than or equal to 0 always. So now, can this happen? The question is, the moment this thing happens, this other thing cannot happen. That is the conclusion. That is why this is a characterization. So let us see why this cannot happen. Once you have another psi like this, you can restrict, this psi to Ux prime to a smaller neighborhood. We may assume that psi, nth coordinate of this psi x of whatever this one is positive for all y inside this smaller subset by continuity of psi. If once it is positive in a smaller neighborhood, it will be positive for all the points in that neighborhood. That's all I am using. And this Ux prime is contained inside Ux. This will imply that Vx prime is an open subset of Hn, interior of Hn now, the smaller set. And hence, any subset of open subset of interior of Hn is open inside Rn because interior of Hn is open inside Rn. Now consider f equal to phi composite psi inverse. from this open subset, they are all inside our Vx prime is inside, where it's inside x, right? Inside x. So psi inverse of phi come back to F2, this one. So now what you get is, this is inside Hn, which is a homeomorphism. But by Brouwer's invariance of domain, it follows that f of Vx prime, remember Vx prime and f of this one, these are both subsets of now Rn. This part is in Hn, this part is strictly inside interior of Hn. Okay, so f of Vx prime must be also open subset, right, and is contained inside Hn. But this contains a point phi x which has its nth coordinate 0. So that is absurd, because an open subset of Rn contained inside Hn cannot have a boundary point there in Rn minus 1. The moment Rn minus 1 hit, if you take any open disk around that point, it will flow out. There will be nth coordinate will be negative also for some points. So it will go out of Hn, right? So that is absurd. Okay, so that is not possible. So the conclusion is that the definition of boundary of X as well as interior of X is now well defined thanks to Brouwer's invariance of domain. It follows that U hat, which is just a notation, take phi inverse of Rn minus 1 cross 0. Okay, so this may be empty, but right now I am assuming that the singleton X is already there. So U hat will be a neighborhood of X. This is now, homeomorphic to some open subset here, because phi inverse Rn minus 1 cross 0 intersection with whatever neighborhood we have, that will be an open subset of Rn minus 1 cross 0. So I am taking phi inverse of that. It's a neighborhood of X inside boundary of X, because all these points in U hat are coming here in the Rn minus 1 cross 0. So they are qualified to be inside boundary of X. Okay. So what I am talking is starting with a phi like this, okay, Ux and phi, where X has gone to a point inside Rn minus 1 cross 0. The point phi n of X is 0. With that, you take phi U hat equal to phi inverse, that will be a neighborhood of X inside boundary of X, and homeomorphic to, by the same phi will give you homeomorphic to an open subset of Rn minus 2, which just means that the boundary of X itself is a manifold, pure manifold in the older definition, okay, of dimension 1 less, namely n minus 1. Okay, this is if it is non-empty, that's all. Otherwise, of course, empty is allowed. Okay, and this boundary of X itself will not have any boundary, because now it is a pure manifold. This is not a half space now here. It is Rn minus 1. Okay. An easy consequence of this observation is that boundary of a manifold with boundary is a topological invariant. What is the meaning of that? If you have a homeomorphism f from X to Y, X is a manifold with boundary, then Y will be a manifold with boundary, and f of the boundary of X will be equal to boundary of Y. You think about it, this is not difficult at all. Okay. So boundary always is mapped onto boundary of Y by the homeomorphism. So restricted boundary of X, it will be homeomorphism again. Now I come to again this nomenclature about manifolds somewhat apologetically. Strictly speaking, our first definition of manifold should have been manifold without boundary, right? And the second one here should have been named manifold with or without boundary. The only problem is, right from the beginning, before defining the manifold, I have to define what is the with boundary and without boundary. So one doesn't like that one. The second point is there is a standard convention of using the smallest words to represent the most commonly used concepts. So we will be studying manifolds, and quite often without boundary. So that should be just called as small as. So we have called that one as manifolds. Okay. So that is all explanation for why we are making this one. In any case, if there is an initial confusion about this, what is a manifold, what is a manifold with boundary, what is a manifold without boundary, having spent sufficiently enough time now, explanation, I hope this confusion, if at all, has disappeared now. Okay. Let us have some examples. Any closed disk in Rn is a manifold with boundary. So we have to prove that one. Since any two of them are homeomorphic to each other, it suffices to show that the standard unit disk Dn inside Rn is an n-manifold with boundary. In fact, boundary itself will be the n-1 dimensional sphere, all x such that norm x equal to 1. Okay, we will prove that. Let us look at first the case n equal to 1. Then this closed disk is nothing but -1 to +1, the interval, right? You can write it as -1 to 1 open union -1 open comma 1. Okay, I have written it as two open subsets of this closed interval. Each of them is clearly homeomorphic to 0 to infinity, 0 closed, infinity open, and that is H1. So I have given a atlas. There are two charts here. Okay, so I have given an atlas. Over. In the general case, what I will do, instead of subtracting this one and adding this one and so on, there are two of them, I will do this one, dn minus the top point, the north pole, whatever, 0, 0, 0, 1, and dn minus the bottom part, 0, 0, 0, minus 1. So this is similar to that, but in n-dimensional version. Okay, and we claim that these two open subsets of Dn are homeomorphic to the entire of Hn, just like this one. Okay, carbon copy of that one, n-dimensional version, that's all. So let us denote shorter notation, n equal to 0, 0, 1, and this point will become minus n. Let us consider one of them, u equal to dn minus this capital N. Okay, this one. The other one is homeomorphic to this one by just taking the nth coordinate, x going to all other coordinates same, nth coordinate as a reflection, right? So it is enough to show that this is homeomorphic to Hn. All right. So we have a ready-made map here actually. Only thing is we have to see how to use it. All right. So first what I do, I will identify this disk Dn with a subspace of Rn plus 1. Indeed, a subspace of Sn itself. See, Sn is sitting Rn plus 1. This is inside Rn. So I need one more coordinate. I will put it in the first one here, or the 0th coordinate. The rest of the coordinates are exactly as x1, x2, xn. Okay, the 0th coordinate is 1 minus summation xi square and take the square root. Why I have done this? If you take now squares of all these, that will be equal to 1. So I will be inside the unit sphere here in Sn plus, in Rn plus 1. Okay, that's all. Clearly this is a continuous map. It is actually the graph of this function. Okay, this function x1 x2 x1 going to that, you take this f is just like x comma this one, so it's like a graph. Okay, so you can rewrite it as y1 y2 yn plus 1. Put fn, okay, equal to 0 0 0 1. Okay, that is n prime. This n prime is a notation. F of capital N is nothing but 0 0 0 1. I am not defining this part. This n prime is just another notation. It follows that f defines a homeomorphism of dn minus n. The whole thing is defined in the whole one. If you throw away that, it will be a subset of b minus n prime, where b is set of all y is in Sn. The first coordinate y1, this part, is greater than or equal to 0 now. This is a positive square root. So this is not the full Sn. It is only half the sphere, right, given by the first coordinate greater than or equal to 0. So this is the preparation I have made now. Now what I do? I take the stereographic projection. Stereographic projection is defined from Sn minus this n prime, the north pole, to the entire of Rn. So that's a homeomorphism. We have studied this one carefully. Restricted to the half disk, it will go into the half disk H here, half space H here, namely y1 y2 yn plus 1, okay, inside Rn plus 1. The y1 coordinate is always greater than or equal to 0, but the last coordinate yn plus 1 is 0 because it's stereographic projection. So this is clearly homeomorphic to Hn. The only thing is, instead of last coordinate yn greater than or equal to 0, I put y1 greater than or equal to 0. So you have to interchange those two coordinates. So look at these methods. I mean, these are important methods inside handling various subsets of Rn. That's all. So more generally, any convex polyhedron in Rn being homeomorphic to Dn is an n-manifold with boundary. Details are left to you as an exercise. Why? I don't want to get into what is the definition of convex polyhedron and so on. If you don't know, you will have to learn it somewhere else. That's all. That is not central to the theme of this course. Note that the manifold boundary of Dn and its topological boundary as a subset of Rn coincide. Namely, they are the unit sphere, right, in both the cases. Indeed, this explains why the term boundary is used in general topology. Classically, these manifolds were defined and studied even without definition perhaps, even before the point-set topology was conceived. Forget about the boundary of a subset and so on. So the boundary of a subset, that concept is a copy from examples like this. Okay, unfortunately we are learning it the other way around. For the same reason as for manifolds without boundary, manifolds with boundary are also metrizable and hence paracompact. Why? Because we have assumed second countable, Hausdorff, and whether they are inside homeomorphic to open subsets of Rn or Hm, they will be locally compact. Okay. So they are T3 second counter T3 space, those are metrizable. We shall often use the word manifold to mean manifold without boundary, the old definition. Okay. So that is why this is a short term manifold. Often the results that we state for them are valid for manifolds without boundary as well, though we cannot take them for granted. There are some results which are not true at all, and if they are true, you have to prove them separately. Sometimes it requires quite a lot of effort as compared to manifolds without boundary. Okay, whenever things are not true at all, we will try to mention them separately. Okay. So here is an easy consequence of existence of partition of unity, because they are, we have shown that they are Hausdorff and paracompact. Okay. We shall now obtain the so-called Collar neighborhood theorem, which is a very useful result on its own. So that is an important result about manifolds with boundary. So let me make a definition first. Let X be a manifold, boundary of X non-empty now. Okay, otherwise the rest of the definition is vacuously true. It doesn't hold at all. So start with the manifold with boundary non-empty. By a collar neighborhood, or simply you can say just a collar of boundary of X inside X, we mean an open set U, okay, open subset of X, okay, with a homeomorphism phi from U to the boundary of X product with 0 infinity. This is a topological product now. Boundary X is subspace of X. Okay, you must have a homeomorphism with one extra property, namely for all X on the boundary, phi of X should go to X comma 0. Okay, there are U is a neighborhood of boundary of X, so boundary of X is sitting inside here, right? So for those points, phi of that must be just X comma 0. So such a open subset, open neighborhood with a homeomorphism will be called a collar neighborhood. Now there is nothing special about the choice of this half open interval 0 to infinity. You could have taken 0 to epsilon, because we know 0 epsilon is also homeomorphic to 0 infinity. That's all. Indeed, once U is a collar neighborhood as above, you look at these subspaces, namely phi inverse of boundary of X cross 0 to R. Take the inverse image. That will be another open subset which will contain boundary of X, and it will be again homeomorphic to boundary of X cross 0 R, obviously, which you can compose with another homeomorphism, make it 0 infinity to satisfy this definition. For Hn, the entire Hn itself is a collar for boundary of Hn. Obviously, Hn is a manifold with boundary, right? So what happens in the case of Hn? Its boundary, has a neighborhood which is the whole of Hn. That Hn is homeomorphic to Rn minus 1 cross 0, mainly boundary of Hn cross 0, cross Rn minus 1. Okay, so this is a neighborhood, the whole Hn is a neighborhood of this one. Similarly, if you take the Dn minus a concentric ball is center 0 and radius r smaller than 1, of course. Okay, take a ball of radius r, closed ball, subtract it. That is a collar neighborhood for boundary of Dn, that is namely the sphere Sn minus 1. Okay, for an interval a to b, okay, closed interval a to b, a to t union s to b is a collar neighborhood of boundary of AB. What is boundary of AB? Where AB is an interval, closed interval, little a comma little b, right? Just the two elements. Okay, that has a neighborhood like this A to T, comma S to B, where T and S are like this, namely A less than T less than S less than B. So that's the example. Now here is the final theorem. So pay attention. Let X be a manifold with non-empty boundary and W contained inside X be a proper open subset in X such that boundary of W is contained inside W. I don't want this W to be the whole of X. Okay. Then there exists a Euler neighborhood U of boundary of X such that this U is contained in U bar contained inside W, and the complement X minus U is homeomorphic to X again. So throw away the Euler neighborhood, whatever left out is again homeomorphic to the manifold itself. Okay. The Euler is always like boundary cross an interval, right? So you remove the open, half open interval. So that will be again homeomorphic to X. That is the meaning of this one here. And such neighborhoods can be chosen as small as you please inside an open set. This W itself is a neighborhood. Okay, then you can take U inside that. Just a U bar is inside W. Alright. So the proof is slightly longer but not difficult if you understand what is going on. The two examples, three examples, etc., whatever I have given, they are the guiding principles here. That's all. Look at what happens in the case of 0 to say 1. Okay, open. So 0 is the interval, 0 is the boundary. It has a neighborhood. No matter how small you take, 0 to some epsilon, which is homeomorphic to 0 to infinity. If you remove 0 to epsilon, whatever is left is again a closed interval, proper closed interval, not a singleton. So it will be again homeomorphic to the whole of 0, 1. Right? Okay, similar to that is what is happening. But we have to work a little harder here. We need to use partition of unity also, because we are not assuming compactness. If you assume compactness, you can probably write down a much shorter proof. Over to you after you learn this proof. That will be left as an exercise too. Okay. So the idea here is a very, very beautiful idea here. What we do is, okay, we attach an external Euler to X. I am going to explain what is the meaning of this one. Namely, you are taking a larger space, you are creating a space, larger space, containing X. Okay. So the rest of the extra space is boundary of X cross in interval -1 + 1, -1, 0. So that is what I am going to do. So I am taking Y as the quotient of disjoint union of X and boundary of X cross -1, 0. If you take disjoint union, that is not much fun. What I do, I identify boundary of X cross 0, this copy, with the boundary of X here. Okay, by identify X comma, X belong to here with X comma 0 here. Okay, the rest of them is floating outside. Okay, observe that Y is also an N-manifold with its boundary homeomorphic to boundary of X cross -1 this time. So this portion becomes the boundary now. All the points X comma 0, they have become interior points. Right? The idea is to define a homeomorphism F from X to Y, which is identity outside this W prime, and then take u equal to f inverse of boundary of x cross minus 1 to 0. Clearly, then u bar will be contained inside w, and x from here to here is a homeomorphism. Okay. So, what is this w prime? I will explain. This is a smaller subspace of w chosen right in the beginning like this. We can choose an open subset w prime such that boundary of x is contained inside w prime, contained inside the closure contained inside w. So, here I am just using regularity, and this one is a closed subset. Closed subset contained in open subset. In between you can introduce this another open subset, right? So, now we begin with a countable partition of unity theta I. How did you get countability? Because the whole space is second countable. Where I am working on boundary of x, which is a manifold. So that for each I, the support of theta I is compact. So this is one of the remark which we made, because of the local compactness. Okay, you can assume that the support of theta i's are compact. Okay, and is contained in a coordinate open subset ui. The coordinate subsets can be assumed to be such that their closures are relatively compact. Closures are compact, right? And if this is this support of theta is contained inside this one, it will be automatically, being a closed subset, will be compact also. Okay. So how do I do that? Start with a coordinate cover, namely atlas. Go to a locally finite cover because of paracompactness. After that, go to a countable cover because of second countability. Use the partition of unity which exists because of paracompactness. Automatically you will get these ones are compact. Okay. So these are coordinate neighborhoods. So I have phi from ui cross 0 1 to vi. See, these are coordinate neighborhoods for points inside boundary of x. Okay. Now I am going inside the manifold x itself by using that these are all neighborhoods of, this whole thing is a neighborhood of this w prime is a neighborhood of boundary of x, and ui's are compact, ui bars are compact. So I can extend this neighborhood to 0, 1, right? Phi from ui cross 0, some. See, this is the first thing here. Because of the compactness, you can extend it to a small neighborhood 0 to 1 to vi. It's Valle's theorem. Okay, homeomorphism phi to some Rn is there. Now Rn minus 1 is there. Now you can take an open subset in Rn. Okay, on open subset vi's, these vi's are inside w prime of x. Everything is working inside of it, such that the phi cross 0, 0th coordinate x comma 0 is x inside vi prime for all x. So these ui's, phi's, I am actually writing as a parameterization. They are parameterizations for points inside the boundary, but the parameterizations occurring for neighborhoods inside x itself. Okay. So you choose such homeomorphisms, there is no problem. Now comes the construction. So this is all preparation, how to choose these things, etc. Now put eta not equal to 0. I am going to do some inductive construction. So its starting point, you don't do anything, eta not equal to 0. Eta k is the sum of theta i's up to k, I range to 1 to k. Remember, these are just non-negative real valued functions. So you can just sum it up, finite sum I have taken. And for k greater than equal to 1, that is the definition. Next, put this zk is a space x comma t such that x is inside uk. So u and u to uk's are open subsets of boundary of x. x is inside uk, the t varies between minus of eta k minus 1 to 1. After all these eta k's are taking values between 0 and 1. Okay, so I take minus of this less than equal to t less than equal to 1 up to there I have. So this is some interval strictly contained inside minus 1 to plus 1. This part is plus 1 on the positive side. The negative side, how much you can go? At the most minus 1. Okay. So these are subspaces of now uk cross minus 1 to plus 1. Okay, but much smaller. So x must be only here. Now zk prime is all xt such that the same thing, but use eta k here, eta instead of eta k plus 1. So since eta k is slightly bigger because one more function has been added here, this will be slightly larger interval than this one. Only on uk. So these are defined only on uk. Alright. Now take alpha k from zk to zk prime be the homeomorphism which linearly stretches the segment singleton x cross this interval to this interval. Linearly stretches means what? 1 goes to 1, eta k minus 1 x goes to minus eta k of x. We have linear homeomorphism mapping any interval ab to a prime b prime, right? So take those homeomorphisms. For each x you do that automatically, because you can write down the formula in terms of eta k minus 1 and eta k here. So it will be automatically a homeomorphism on the whole space. Okay. So put yk, see again I am defining these things inductively, right? Put yk equal to x union this x comma t, where eta k is taken up to 0 only. Okay. So portion of zk is taken, zk prime is taken only up to t less than equal to 0. Okay, that is your yk. Namely, these are extra spaces, you see, that's what I have taken. Okay, but take it with union with x. Okay, so they are all subspaces of y now. Let beta k from zk prime to yk be the embedding given by beta k of xt is phi k of xt where t is positive. Remember, this phi is ui cross 0 1, so the second coordinate is here non-negative. So that is what you have to do. So non-negative you take phi k. When it is negative from 0 minus 1 to 0, you take it as xt itself. Okay, identity map itself. So that makes sense because they are all subspace. We are working inside y now. So it will go inside yk because this beta k is defined only up to minus eta k. For t negative, not less than equal to 0, you define this. When t equal to 0, the two definitions coincide. Okay. So we have got these embeddings of zk prime inside yk. We define gk on the image of beta k intersection with yk minus 1 to yk by the formula gk of beta k of xt could beta k composite alpha k. This alpha k is stretching the smaller space to a larger space. Okay. So first stretch it and then take beta k. Every member here is the image, so it is beta k of xt. Okay. So take that xt, stretch it, and then again take beta k. So it is like first you take beta k inverse. Instead of writing inverse, I have just written gk of every element here is after all unique element like this, beta k of xt. Okay, if you write it as some y, then this xt will be beta k inverse of that. So that is more confusing than writing. So this write like this. So gk is defined like this. Okay. If x is not in the support of theta k, then eta k will be 0, right? So if eta k is 0, what is this summation? It will be eta k minus 1. So that point will be inside zk, not in zk prime. It will be here. Though I put this one, okay, for points wherein x is not in the support of this theta k, eta k is eta k minus 1. Therefore, alpha k of xt will be just xt. Therefore, gk of beta k of xt will be beta k of xt throughout. Outside, for negative things, it is just xt, all both of them are xt. But now because of this one, gk of beta k of xt will be just beta k of xt, because this is identity. So the stretchings are extending one from the next one. That is important. Okay. Now we define fk from yk minus 1 to yk. See, on subspaces, this beta k's we have defined. Okay. Now for the whole full yk to be gk on image of beta k and identity outside image of beta k. Okay, so this is very important here now, because these things are just stretching things, right? So on whenever it is minus equal to plus 1, it is identity already there. Okay, so on the plus 1 it is identity. So also when theta k is 0 for points which are outside the support, these two are the same also, right? So therefore what happens is, that is an important point. The point is that once you are outside this image of beta k, okay, on the boundary of beta k itself, which is 0, therefore on the outside of this one, so you can just define it as identity. So extend it identically, then it will follow that fk is continuous. Indeed, since each alpha k is a homeomorphism, it easily follows that fk is also a homeomorphism. Finally, there are infinitely many of them. I am putting f equal to the compositions of these fi's in that correct order. Okay, the reverse order. So what is the meaning of this? How do you explain that? Look at any point. Okay, f1 is defined, f2 is defined, f3 is defined. After a certain stage, it will become identity. Why? Because this fk, once the point is outside theta k, outside the support of theta k, this fk will be just identity. So you are taking only the composition up till here, stretching along these intervals, vertical intervals. X will be fixed, x comma t goes to x comma t prime. That is the kind of homeomorphism we have here. Okay, so this makes sense because at each point only finitely many functions are not identity. After that it's identity. So this is like infinite product when you take most of them equal to 1. Infinite product of elements, I mean real numbers, that's similar to that. Okay, so note that the complement on the complement of V, which is phi I union phi I of ui cross 0 1, take the union, and therefore outside W prime f is identity. On V itself, f makes sense since any point x belongs to boundary of x, there are only finitely many I for which x belongs to ui, and this is like local coordinate, locally finiteness and so on. Okay, and fk of xt is equal to xt if x is not in uk. X is not in the support of theta k, then already this fk is identity. But these things may be, so they are all inside. Once it's beyond uk, there is all theta k's are, so theta 1, theta k are all 0. That's the whole idea. Indeed, in a neighborhood of x, all fk are identity except those k for which theta k is not 0. Right? So that is the whole idea. So for this reason, the map f is also proper map. Proper map. Why? It is outside. You take any point here, there will be neighborhood, which is a compact neighborhood, and outside that it will be identity. So it goes on like that. Okay. So only at each you have to take some compact neighborhood of boundary of x. Okay. Then the rest of them, this point, you can use this formula, it will be identity. So the changes are occurring only inside a compact neighborhood. For each compact subset, you will get a compact subset of, for each compact subset of boundary of k, you will get a compact neighborhood, something 0, 1, minus 1 to plus 1. Inside that, everything is working here. Outside that, it will be identity. Okay, so for this reason, f is a proper mapping. Summation theta k is 1, it follows that f will be surjective. Summation theta k is 1, if you have anything less than 1, it will be hit in some k, then yk to that yk plus 1 will contain that. Okay, so it will be a surjective mapping. Okay, stretching after 1 will be also hit there from some point. Given any x, some summation finitely many sum, this summation though it is infinite sum, given any x, there will be finitely many coordinates, theta i's, for which summation theta is equal to 1. You look at maximum of these theta i's, at that point the point x comma 1 will be hit. So that is why it is surjective. Since each fk is an embedding, f is injective also. Therefore, f is homeomorphism. A proper injective, okay, surjective map. That's why it is, and it's an embedding. For each embedding means what? Open map or closed map. You can use this in open mapping. Okay, to see open mapping, you have to restrict, take an take a point, take a neighborhood, compact neighborhood. Okay, inside that only finitely many compositions are there. They are all open. The composite is open. So all these study. So this means that f is homeomorphism. Okay. Yeah. So that completes the proof that we have Euler neighborhoods for the boundary of x, the entire boundary of x. Whenever boundary of x is non-empty, of course. Okay, here is a easy exercise. Show that a manifold with boundary is connected if and only if its interior is connected. This is a slightly tricky thing. You have to think about this. Interior is connected. Of course, interior is connected, but what about the points on the boundary? Why the whole thing is connected? That's what you have to show. Okay. But that will make you think, what exactly should I use here? All right. So next time we will do some more properties of manifolds. Mostly we will now deal with only manifolds, that is manifolds without boundary. Thank you.